Today, I will talk about all-optical magnetization switching and specifically about application of this effect for high-speed optical memory. The all-optical magnetization switching describes the effect of magnetization reversal of ferromagnetic material when light illuminates it. Since a ferromagnetic material has two stable magnetization states, the data encoded in optical pulse is memorized within ferromagnetic material. As you can see in this animation, the light which is emitted by a laser reverses the magnetization direction in a focusing spot. The video is divided into three parts. In this part, I will describe the details of three known mechanisms of all-optical magnetization reversal, which are magnetization switching assisted by external magnetic field, photon-to-spin conversion, and the toggle switching. I will describe three existing mechanisms of magnetization reversal by light. The first mechanism is the magnetization switching assisted by external magnetic field. In this case, a light pulse triggers the magnetization switching and the magnetization is reversed along the direction of externally applied magnetic field. The second mechanism is the magnetization switching by circularly polarized light. In this case, the magnetization is switched up and down accordingly whether the polarization of light pulse is left or right circularly polarized. The third mechanism is the toggle switching. In this case, the magnetization is switched into the opposite direction independently of the initial magnetization direction or the polarization of light. The first mechanism is the magnetization switching assisted by external magnetic field. This mechanism has been used for data recording in a MO disk which were very popular as data storage about 10 years ago. For such a recording, a laser beam is focused into a very small spot on magnetic disk. An external magnetic field is applied in direction corresponding to the recording data. For example, magnetization up corresponds to 1 and the magnetization down corresponds to 0. This slide explains operation principle of this mechanism of recording, which is based on heating of a recording area above the Curie temperature. As a result, the illuminated area fully demagnetized, which means that each individual spins are directed in absolutely random direction. Then, when the area is cooling down, the spins are aligned along the external magnetic field, and the data is memorized. It shows a carrier image of surface of a MO disk with recorded data. A white area corresponds to magnetization directed up, and a black area corresponds to magnetization directed down. As you can see, it is possible to store a lot of data in magnetic disk by means of modulation of magnetization direction. Next, I will explain the second mechanism, which is a magnetization switching by a circularly polarized light. In this case, the magnetization is switched up or down accordingly whether the polarization of light pulse is left circular or right circular. For example, the left circularly polarized light always switches the magnetization into up direction, and the right circularly polarized light always switches the magnetization down, independently of the initial magnetization direction. For example, if a quarter wave plate is placed just below of laser which has a linear polarization, the angle of wave plate switches the polarization between left circular, linear, and right circular. When the light polarization is right circular, the spin on the focusing spot toned down. The linear polarization does not affect the spins at all, and the left circular polarization tones the spin up. It means that the data recorded into the magnetic material correspond to the data encoded into the polarization of light. This slide shows a carrier image of gadolinium iron cobalt film. Again, the dark area corresponds to the down direction of the magnetization, and white area corresponds to the up direction. This image taken before explosion by light. Dark and white areas correspond to static magnetic domains of the opposite magnetization. Next, light of right circular, linear, and left circular polarization was scanned through the area. As you can see, the whole area where the right circular polarized light was scanned became of white color, meaning that the magnetization direction in this area is up. Therefore, the right circular polarized light turns the magnetization up independently of initial magnetization direction. The whole area where the left circular polarized light was scanned becomes of black color, meaning that the magnetization direction in this area is down. Therefore, the left circular polarized light turns the magnetization down independently of initial magnetization direction. As the linear polarized light just demagnetizes the material, it is the same sample, but the scan is very fast so that each pulse illuminates a separate area. The result is the same. The right circular polarized light turns the magnetization up, and the left circular polarized light turns the magnetization down independently on the initial state. This slide explains the physical principle of this mechanism of recording. A circularly polarized light has a momentum. A circularly polarized photon has a spin equal to either plus or minus 1. The spin of the photon transforms into the gas of conduction electron, polarizing the spin of the electrons in one direction, or the same, creating the spin-polarized conduction electrons. The spin-polarized conduction electrons interact with the localized d electrons, turning the spin towards its own direction. As a result, circularly polarized photon turns the spin of the ferromagnetic material along its own direction. This slide shows the path of how the momentum from light is transformed into the recorded data in a ferromagnetic material. A circularly polarized light is effectively absorbed by conduction electrons, making the electron gas spin polarized. Or if it was already spin polarized, the light changes the direction and amount of the spin polarization. Due to a moderate interaction between conduction and localized d electrons, spins of localized electrons turn along the spins of conduction electrons, which leads to reversal of the magnetization and data recording. Next, I will explain the third mechanism of light-induced magnetization reversal, which is called the toggle switching. In this case, the magnetization is switched into the opposite direction independently of the initial magnetization direction and independently of the polarization of light. It means that if initial magnetization direction is up, the light pulse turns it to the down direction, and if the initial magnetization direction is down, light switches it to the up direction. This slide shows again a carrier image of gadolinium iron cobalt film of different composition. The upper row shows the case when initially the film is magnetized in up direction. The lower row shows the case when initial magnetization direction is down. Here, the first pulse turns the magnetization up, the second pulse turns it down, the third turns it again up, and so on. The case of initial down magnetization is opposite. The first pulse turns the magnetization down, the second turns it up, the third turns it again down, and so on. It means that when a laser illuminates the magnetic film, all spin within the focusing spot turned into the opposite direction. Next pulse turns the spin back, and next pulse turns the spin opposite, and so on and so on. The physical mechanism of this type of magnetization reversal is more complex. If the first and second types of magnetization reversal may occur in any ferromagnetic material like iron or cobalt, the third type can occur only in material which is called the compensated ferromagnet. The compensated ferromagnet, like iron terbium, is a compound of two metals. Each metal has a different symmetry of the localized electrons. For example, symmetry of iron electrons is a d-type, and the symmetry of terbium electrons is a f-type. This material has two spin lattices. In each lattice, all spin are aligned in one direction. There is a weak antiferromagnetic interaction between the iron lattice and terbium lattice. As a result, all spin of terbium electrons are opposite to the spin of iron electrons. Such a complex alignment of the spin is due to the properties of exchange interaction, about which you can read in this my web page. The exchange interaction is only strong between two very similar electrons. The property is a direct consequence of the origin of exchange interaction. As a result, there is a very strong ferromagnetic exchange interaction between identical d electrons of iron, and a similarly strong ferromagnetic exchange interaction between identical f electrons of terbium. However, the antiferromagnetic exchange interaction between iron and terbium is weak, because the d and f symmetries are rather different. Next, I would like to explain about the difference between the efficiency of light interaction with df and conduction electrons, and specifically about the importance of electron size. The quantum mechanics states that the most efficient interaction between two objects is in the case when the size of two objects are about the same. The size of photon, which is focused into the small spot, is about 5 micrometers. The size of conduction and valence electron is between 10 and 1000 nanometers, depending on the crystal quality of a material. As a result, the light interaction with conduction electron is strong and effective. The size of localized d and f electron is about the orbital size, which is about 0.1 nanometer. As a result, the light interaction with d and f electrons is weak and inefficient. This fact can be easily verified just by looking at the absorption spectrum of any material. The absorption due to the conduction and valence electrons is broad and strong. The narrow absorption peaks of d or f electrons are tiny and barely distinguished. Additionally, there is a moderate interaction between conduction and d electrons, and rather weak interaction between conduction and f electrons. It is because the sp symmetry of conduction electrons is rather different from f symmetry. As I mentioned before, there is a weak antiferromagnetic interaction between d and f electrons. Therefore, when light is focused on material, it mainly interacts with conduction and valence electrons. As a result, the temperature of gas of conduction electrons increases substantially. Because of moderate interaction of the d electrons and conduction electrons, the temperature of d electrons increases, but not as much as the temperature of the conduction electrons. There is some heating of the f electrons, but it is very weak because of very weak interaction of f electrons with conduction electrons and d electrons. This fact is very important for understanding the toggle mechanism of magnetization reversal. Now I will explain the physical mechanism of toggle switching. The iron terbium consists of two spin systems, the iron and terbium systems, which are antiferromagnetically coupled. Along each system there is a magnetic field which is shown by an arrow of corresponding color. In equilibrium, two magnetic fields are opposite to each other. The light pulse is hitting mainly the iron spins almost without hitting of the terbium spins. As a result, the temperature of iron electrons exceeds the Curie temperature and the iron spins are demagnetized. In contrast, the terbium electrons remain cool and keep the spin direction. Consequently, the magnetic field along iron spins vanishes and the magnetic field around terbium remains. When iron electrons are cooling down, the spins are aligned along the only existing magnetic field, which is the terbium magnetic field. Therefore, the iron spins are aligned parallel to the terbium spins. However, there is antiferromagnetic exchange interaction between iron and terbium. Since there are more iron atoms, the antiferromagnetic exchange turns the terbium spin to be opposite to the iron spins. In total, the optical pulse fully reverses the magnetization. The magnetization direction always changes to the opposite, independently of its initial state. This is animation of how each spin behaves during the toggle switching. The green and purple balls show the iron and terbium spins. The arrows show the intrinsic magnetic field around iron spins and terbium spins. A laser pulse demagnetizes the iron spins, meaning that the iron spins are distributed in all directions, while terbium spins remain in one direction. During cooling, the iron spins are aligned along the magnetic field of terbium. Next, the terbium spins are rotated to be opposite to the direction of iron spins. This slide shows experimental evidence which proves the described mechanism of the toggle switching. The spin direction of each specific element can be measured by XMCD method. The XMCD measures the difference in the X-ray absorption between the left and right locally polarized X-ray, which is proportional to the spin. Turning X-ray wavelengths to the absorption edge of the specific element, the spin direction of only this element is measured. This graph shows the time evolution of spins after a short optical pulse triggered a toggle switching in gadolinium iron cobalt film. The gray circle shows the spin direction of gadolinium and white circle shows the spin of iron. Two graphs show the same data but with different time scale. The iron spin quickly demagnetized and next is aligned along the magnetic field of gadolinium spin. The gadolinium spin is demagnetized only a little and next is aligned slowly opposite to iron spin. The mechanism is exactly the same as was described in the previous slides. It is the end of part number 1. If you are interested, please go to part number 2, in which I will talk about the benefits of high-speed photon-to-spin demultiplexing. You can find the link to part number 2 in description just below this video.